All, and today we'll see some nice problems on matrices, especially the properties related to adjoint of matrix, which is very frequently asked in mains and advance. So here we go with the first one. I'll try to give you multiple approach of solving these problems. First one is determine all matrices A belonging to M3R, which represents 3 cross 3 matrix with real entries such that adjoint of A is given as follows. Now, one of the most useful identity in matrix algebra is A into adjoint of A is that of A into I, and that's exactly is being used there, as you can see in the first line. Now if I'll take that on both sides, so that of A into B, if it is a square matrix of same order, can be written as that of A into that of B. So using that, I got relation that of A cube minus 4 that of A equals 0, because you can write this as that of A times that of adjoint of A equals that of A is a number, so that is that of A whole cube, where again the property that of K A is K to the power n that of A. So I use this matrix property, and hence we got three possible values of determinant, which is 0, 2 or minus 2. Again we can calculate adjoint of A, so that can be written as, if I replace A with adjoint of A in the identity, A times adjoint of A is that of A times I. Here I3 represents identity matrix of order 3. So we'll get this identity, and using that of adjoint of A is 4, because adjoint of A is given, so we can calculate that on both sides, and this calculation will give you 4 over here. So that gives you that of A times adjoint of A is 4 times A, where in the third step what I have done is pre-multiply with A on both sides. So now we are having either that of A is 0, which will definitely give you a contradiction, because that implies 4A equals 0, hence A is null matrix. But since adjoint of A is non-zero as given in the problem, hence that is not possible, right? So now I'm left with other option. If that of A is 2, then 4A equals 2 times adjoint of A, and hence A we can write as adjoint of A times half. If that of A is minus 2, similarly A is minus half of that. Now since adjoint of A is a matrix which is given in the problem, so we can easily calculate this adjoint, and we'll get two possible answer for this problem. So there are only two matrices which will satisfy this condition. Of course, they can ask you as cardinality or number of elements in the set in multiple choice examination. Let's come to second method, and here I have used the property that that of A inverse is 1 by that of A, and if A is a matrix, square matrix of order n, that of lambda A is lambda n, that of A, where lambda is any complex number, right? It can be real complex. So we can use the well-known formula of A inverse is adjoint of A by that A. To see 1 by that A value is that of adjoint of A by that A to power n. So in our case, n equals 3, because we are interested in a square matrix of order 3. Hence that A will be plus minus 2 over here. So basically, since adjoint of A is that of adjoint of A is 4, same as above. So what we can do is that A is square will be 2 by the properties. So that gives that A as plus minus 2, right? Now we can go again back in the formulas, and from here adjoint of A is known, that of A is known. So A is known. So we can inverse this to find A is plus minus 2 adjoint of A inverse. Since adjoint of A is given, so adjoint of A inverse can be written, because to find A inverse again, you find the adjoint of that and its determinant. So using that property, we will get adjoint of A inverse as this, and hence A is plus minus of this. Still there is another method where the similar way adjoint of A is that A n minus 1, and in our case n equals 3. So that of adjoint of A is 4, and adjoint of A is adjoint of A converted into adjoint of A inverse, right? That directly follows from the A inverse theorem, which equals adjoint of A by that of A. So यहाँ से if we'll keep this, you'll get a nice identity, which is adjoint of A is that A to the power n minus 2. This you can prove again from fundamental as well. You can write A times adjoint of A equals that of A times I. And now if I pre-multiply this with the adjoint of A, so what we'll get is adjoint of A times A is that of A times I. So that will be that of A times adjoint of A. This result can also be derived differently. We can write A times adjoint of A equals that A times I, the most powerful theorem. Now replace A with adjoint of A. So adjoint of A times adjoint of A is that of adjoint of A, which is that A to the power n minus 1 times I. Now we can pre-multiply with A on both sides. So we'll get A times adjoint of A, that will give you that of A times I multiply with this matrix remains the same. So finally we got adjoint of A equals A times that A to power n minus 2 times I. A times I will just is, so it's A times that A to power n minus 2. Of course in this step I'm allowed to go from there. If that of A is non-zero, it means matrix is invertible. तो वहां से डायरेक्टली एडजॉइंट ऑफ ए विल गेट फ्रॉम व्हिच इमीडिएटली इट follows a equals plus minus 3 to 1 2 to 1 0. Let's try another question, and this similar ideas is very often asked in G advanced, and recently many problems in last NT paper of mains was also of this ideas. So A is a 3 cross 3 real orthogonal matrix. Remember, matrix is orthogonal if A transpose is I, and that's equals A transpose A, right? So according to orthogonal condition, that of A whole square will be 1. So which forces either that will be plus minus 1. In the question, they have explicitly given that A is 1. We have to prove that this expression is an integer number and you have to find the value. So in multiple character examination, they can directly ask you the value of this. One blind way of solving this question will be method 1, where you blindly take a matrix A given by A11, 1, 2, 1, 3 till A33. And if we apply all these data, we'll get sum of trace is sum of elements, diagonal elements. So that whole square minus 2 times this plus. This we can decode as for I less than j. So let's keep j equals 1. Then I is not possible, right? Because I will be 0. So if we'll keep j equals 2, then possibilities of I is 1. Similarly for j equals 3, I can be 1 and 2. If we put all these values, you will get the expression evaluates to this. Since A is orthogonal, so A transposes A inverse. Here I have used Et as A small t, this notation. Taking into account that A is equals 1, we can find the cofactors element, that of cofactor by that of A. And if we'll put all the values, you'll get answer interestingly independent of the matrices given, and it will be 4. This can also be done using Cayley-Hamilton theorem, which is usually taught in the coaching institute. So we know that of A minus Ti can be written as T cube minus sum of diagonal elements, which is trace of a matrix times T square, plus it is the diagonal element cofactors, so which is written over A, and minus determinant of matrix, and determinant of matrix is 1, so minus 1. Now we can multiplying out by that of A minus Ti is basically it will have 3 roots T1, T2, T3, and comparing both expression we can use sum of roots taken 2 at a time. Similarly, sum of roots taken 3 at a time is 1. Since we know data of A is 1, so A will have one eigenvalue which is equal to 1. So we can assume it to be, let's say T1, T2, T3. I assume it to be T1 over here. So the product of other root is basically 1. Again, exactly in the similar fashion, if you evaluate this, you can see by pausing the video, you'll get 4 as the answer for this problem. So I hope it was interesting, and moreover, you understood how we are going to decode this in a different way. So this is exactly how we can go about solving these problems multiple. The takeaway of problem was how in the second problem we have applied Hamilton theorem, which will be useful sometimes, because the version of Hamilton which you read is A minus lambda I, that is characteristics equation, right? That of that equals 0, which will get a cubic in the equation. So if you want these videos of more of such kind to enrich your exam problem solving strategy, I'll come in the next lecture. Meanwhile, I'll also solve some questions from the mock test in some upcoming lectures.